lectures until the end. The first of them comes from Dr. Miro. Wow, I cannot pronounce his name, so I call him Miroslav. He's an assistant professor in Erlangen University in Germany. His specialization are the phosphor materials, and he's going to discuss about laser applications and industrial laser-based manufacturing techniques. So it's very much related with what we listened before, but we're going to view this application from another point of view. I think so. All right?
Yeah, hello everybody. I hope you have enjoyed your lunch, and I would like to thank you very much again for organizer Francesco and helper here, but especially for Kostas for organization of this seminar, and for very clever organization of the program, because my talk is after lunch. After lunch people are relaxed, and I would like not to discuss with you scientific problems. I would like to discuss with you maybe industrial problems, maybe marketing, maybe new development, and so on. We are University of Applied Physics, or maybe Material Science and Engineering. So my name is Miroslav Batentschuk, and I have written my colleague Nahum Travitsky also in the title here, because he has helped me to prepare it. He is a main leading specialist in Germany for additive manufacture technology. Therefore, it's clear I have used several results from Nahum Travitsky. And again, I would like to say about applications. But first of all, outline about our university, short information. And of course, we need only a small part of science today, please. Short fundamentals of laser material interaction. And after that, we make about example of application, very famous, but I would like to mention it today. And main part, and main part will be additive manufacturing technology today. Conclusion outlook, it's absolutely necessary about our university, and in this university we will make the next course. We will discuss about topic. I invite you just now to this course, and the topic will be, of course, partly about additive manufacturing, the topic of mine today, and laser structuring. We will see you several labs and so on, but also we would like to focus on the characterization of material, because we have very strong teams for second electron microscopy, transition electron microscopy, and so on, and you will see maybe results of damage of laser in some elements. Again, University Erlangen is in Bavaria, in vicinity von Nuremberg. Is a university with nearly 40,000 students and nearly 270 years old. Really, I would like to say, according to the latest ranking from Media Reuters, our university is the most innovative university in Germany and is number 5 in Europe. Why? This is a secret, because we try to use, thank you very much, we try to use really very innovative basics knowledge, and then very quickly, we try it very quickly to put it in the products and transfer product to the industry. It's really the secret of innovation. We have a big technical faculty. Technical faculty has several departments. Our department is Material Science and Engineering, and it's a small university, actually. A campus, South Campus in Erlangen is nearly 10,000 students, all technical faculty. And our department consists of 9 chairs. Glass and ceramic, biomaterials, metals, material properties, corrosion of materials, several types, semiconductor and metals, and micro and nanostructure, general property materials in nano and sub-nanostructures, polymers, our electromagnetics and energy technology for development of solar cells, and also just now a new chair material simulation. Welcome in October, maybe end October, start of November. I see you, I think, 70–80%, yeah, in Erlangen. Just now, I have promised very short about fundamentals. My colleague, Dr. Oswald, and for lunch, another talk about perovskite and so on. It was discussed, and yesterday it was discussed about light absorption semiconductors. It's really pleasure. It's really very nice if we make band absorption from valence to electron belts. We can make absorption very thin films, but also it's possible if we make the absorption from donor or the acceptor from valence to acceptor. And in this situation, we will have, of course, nice absorption to make engineering with laser. We should don't forget, and I say you this formula for estimation of quantum size effect, estimation of shift of edge of your semiconductor is really simple, but works perfect. And if you try to make production with laser, some semiconductor, you should remember if you have volume material, nearly 80 angstrom, yeah, it's volume material, or you have 20 angstrom, the shift of is really huge. And if you think about laser in which you would like to make manufacturing, it's critical meaning. But general, if you make with metals and so on, the old good Bert-Lambert law with absorption coefficient, with direction of propagation, and the very interesting optical absorption depth. Here is depth. If you have small depth, it's very nice. You can proceed with laser very successfully. And you have silicon is it's not so strong, but you are in the vicinity of 10⁵ nanometers is also okay for working with, for instance, with IAC neodymium laser 532 nanometers. Yeah, you should remember this picture forever. It is taken from this book, and if you would like to make some engineering with your laser, you should estimate, of course, first of all, the absorption of light in your materials. And also, Dr. Oswald has mentioned today, if you're working only with electrons, with plasma resonance, you should remember there are, of course, plasma resonance frequency. The absorption is a black curve, is not too strong. And of course, there are the region with UV. Be careful with UV laser, or maybe with Fenta laser with very high intensity, because you have 2 photons and you come very quickly to UV. Yeah, because in this situation, your plasma frequency cannot follow the frequency of the electrical field of your laser, and the metal will be practically transparent. So better, of course, to take this type of laser. Just now some examples, very simple example of application. Fantastic book, Field Assisted Sintering, I think 2018 exactly. And all kind of interaction with matter. It was analyzed, also a laser, but very simple for us. If you make organic photovoltaics, of course we should accelerate the solidification of our system, and this is worth to use simple, very simple technique, infrared, simple for solidification. But if you would like to use it again, 40 or 50 years ago, the idea, but if you would like to work with something without crucible, you would like to make really 0 ppm impurities. If you need it for your semiconductor, think about it. You should use laser melting, and you should the pedestal grow technique without contact with crucible. Crucible is really the mass origin of your contamination. Just now to additive manufacturing technology. Actually, it's for me, it is a main topic in which I would like to discuss with you about it. And look, this art things, yeah, it's really not possible or impossible to manufacture it. It's only as model in the computer is okay, but manufacturing is extremely hard, yeah, but it's really nice. It's art, yeah. Also, it's possible to make some pictures by my colleague, Professor Travitsky. Thank you for him, for introduction for this course. But the idea is, why do we need rapid product development with new processes? The idea is to receive the best quality at very short time, and after that you have access. Yeah, there are a row of circumstances of development, and if you read it, you will see the very important decreasing lifetime of products. What is this? It's really it's a process which works because the products lives very short time just now, and we should follow our production technique to make development some similar in this direction. And of course, this point, individualization of products, it's possible with manufacturing technology. Very easy. Just now you will see. Yeah, I think I have maybe 100 samples about it, and I promise this is not science, but also industry mainly. Strategy, your future, of course, you're a future engineer, you're a future leader, you're future management, and also, and you should consider these 1, 2, 3, 4 points. Of course, cost and leadership is trivial, is clear for you. Of course, you always would like to make it. However, it's not easy to make compromise between cost leaderships and differentiation, because individual product is really very expensive. Actually, with manufacturing technology, it's possible to make all kind, from design to functional products. You see different, also sure bikes, part of engines, and medicine, dental. It's also biology. This is biology, part of body, implants. And I would like to explain you, or maybe to present why additive manufacturing and which kind of additive manufacturing technology we have, some examples, a conclusion, and of course future of additive manufacturing. Motivation for materials. It's actually the question how to proceed, how to make very complicated products with very simple procedures. And another part, you should know exactly how to proceed to make this precisely defined systems. And we need fast product formation, as I said, and of course necessary to make time to market. This is a key of development for material science, also for us at least, yeah. And this is extremely important to think and really to make the precise decision. Because if you make a wrong decision, you make development in the wrong direction, and after that you cannot produce something because your product is not suitable with new materials which were developed until now. Yeah. What it was earlier? Earlier it was very simple subtractive process to manufacturing of details, as this one. Okay, you remove all part of materials which you don't need, but the problem is you cannot make very complicated thing. How you can make this mechanical removing this part? It's impossible. It's really impossible, and this machine are necessary to make several systems in the industry. But nevertheless, with additive manufacturing, it's only nearly 20% of costs. The rest of nearly 80%, this is the post-hard machining. This really not all is perfect, as I promised just now. It's very nice, additive manufacturing, but you should make in the same time also the post-hard machining, post-hard manufacturing of whole system. And general advantage as you see. How to proceed? It's 5-step approach. Of course, it's necessary to create a model. Yeah, you create a model. Sorry, it's wrong button. You have a model. Okay. After that, you convert in some format, computer simulated tomography format. After that, you should make thin slices. Of course, it depends from the process or from precisely what you would like to reach. After that, you can print it. After that, you can print layer by layer, layer by layer, exactly your model which you have in your computer. And after that, of course, there is a problem which I mentioned 1 minute ago, cleaning surface post-processing. It's not possible to go away from this post-processes if you have manufacturing technology. Just now, you will say several examples why it's really very important. How it's work and what is the role of laser? You make layer by layer from Dr. Blade technique, for instance, yeah, and put it on the table for production. After that, your computer knows exactly the problem, which place should be solidified, should be heated, and now you can produce your product. Really very simple. Of course, if you look, the fields in which you can use it practically all in the modern science and industry, all. You can use it, your additive manufacturing, in each part, in aerospace, medical, art. You have some example. Also, the modern thin film devices and structures, if you know it, you can make printed. We make it just now for our organic solar cells. We make printed, this partly structured, and we know exactly how to proceed different part of with inkjet printer, for instance. Yeah, there are some samples about it. There is a very nice tree about fields of development of using of additive manufacturing, and we have taken from very nice roadmap. And you see that in electronics and architecture, art, and medical, and so on, practically all kind of industry of kind of science that you have, you can use their manufacturing. In which time it's important? It's important for you as for young people, which will work maybe in the next 20, 30 years. Yeah, sure. Actually, you should estimate the new development, and you should know, okay, in the next 5, 10 years it will be work. And actually, it's a relatively new technique, and of course, you should be sure in the next 10, 12 years it will be used in these fields which I shown in the application tree. As for instance, in our institute, so we have started actually 2005. After 1 or 2 years, we have produced as a small model of engine. And really was very, very high precisely. It was printed in 3D. And of course, it's extremely interesting if people would like to test some mechanical properties, to test some questions which material we should use it. Yeah. Therefore, you can start with small model with such engine, also with mechanical stress, also with heating stress, and so on, so on. Some historical view. It was actually 3D printing several years ago topography. It's really an example. Yeah, you have 2D, and after that you have mountains or seas and so on. And also, look, it was in Paris about 1870. It was measured, actually, the dimension of the head of a man, and it was tried to understand how with several pictures you can make 3D object. Yeah, it's really, the history is very long, but the modern history nowadays actually started from 70s, developed the apparatus for selective solidification of photocarbon resin, yeah, and photolithography processes, yeah. And stereolithography, it was patented in 1986. It's only 33 years ago. It's new. And after that, 1 year later, 3D system first SLA machine. It was development. In the 90s, you have shown the apparatus on the €4,000 dollars. Really on the market, yeah, and just now it's nearly a new explosion of this technique and diffusion of various additive manufacturing technology, as I mentioned, in different fields of science and industry. What is the market? Market, of course, if you are a manager, you should think about systems, material, and service. Of course, just now it's really there are service. There's nearly 1,000 in the world, and materials, of course, it should be different. You will see just now which material we will have, and of course, people start as a new science. Yeah, people start to make your development in several directions. Yeah, what should be rapid prototyping is people make some PhD. Works, and people try to develop tooling and manufacturing practically in the industry more and more. But the critical importance, shorter product lifetime. No? And of course, this growing individuality of products, it's no problem for the factory material. You are free. You make work in 2 days on your computer with computer tomography, and you can develop a new product, of course, if you know how to proceed. There are some examples which were developed at our chair and our institutes. Also, real dimensional engines and small turbines. But the problem is often the reverse engineering, because if you have something, and think, okay, it's very nice, you should of course to measure it. You can measure with laser, you can measure with computer tomography, and so on. And after that, you should make the 3D computer modeling. And after that, of course, you can print. How to print? Just now, we will see. Yeah, is also made in our chair after laser 3D measuring, and it's also to make some figures from the scans. You can use nearly 50 scans, and after that, of course, you can print final model. Just now, more technology. It was really just now advertisement. It was a general speculation. Kostas, excuse me, how much time I have? 20 minutes, yeah? Okay, yeah, it will be enough. Because all slides are on the server, you can read it more carefully, yeah, of course, later. But now I would like to concentrate on the more important things. We are working with powder. We are working often with powder. And of course, interaction with powder is some different as interaction with semiconductor, because we have scattering, because we have several defects, And actually it's easier to use also for isolator, for aluminum oxide, for instance, yeah, to use simple, not femtoseconds, simple laser in nanoseconds in visible region. Of course, it's possible to use extrusion of material, to use materials which are formed with a heated and with a form in special form, just now you will see, and make the printed of this one. And the very interesting thing, inject techniques. Also we can really print as we make it at our chair with organic photovoltaics. Of course, I will show you a couple of examples with sheets. You can for preparing, yeah, your raw material in form of sheets, and after that make the solidification or melting in different place with laser technologies. Yeah, it's also possible to work on the level of gas, but actually it's not on our chair. There are not too much examples about it. You see, there are really several techniques. At our chair, we used powder from printed pasta and wire, also for filament and liquid now, and also sheets. Just now we will see a couple of examples. But actually it's a general or the old possibility how you can use the additive manufacturing in several techniques. Why so many types of additive manufacturing? Because you have several tasks. You have tasks to make quickly, to make very accurate, to make very precise, to make huge dimensions, or make nano or the sub-micro dimensions. And of course, the important thing also the cost. You should think about cost because, yeah, we, at least at the material science and engineering, we think about bridge, about production and development. As this one, yeah, it's also possible to make also in architecture 3D printed. It's not it's a 10-meter dimension. In principle, you have setups. You can make print houses. Yeah, as it was, yeah, as a couple of projects at Technical University of Wien in Austria, the 3D printing, there are, of course, enough experience in this region. There are firms, there are fields of development, and of course there are also a list of materials which use as a rule for these purposes. But the reason for 3D printing is exactly the same as for additive manufacturing, and it is samples which you can do it. You can do it actually each form which you can. And look, you can work also with silicon carbide. As with silicon carbide is not easy to work because the system very high melting temperature. But I didn't propose to make melting. It's enough to make temperature treating after printing. And of course, you can you can use maybe with some flux material between grains and so on, how to make your strong and mechanical stable system. Also, I have mentioned it's possible on aluminum oxide, alumina, to make it, of course, after printing, and after that you should make, of course, thermal treatment. The idea is how to reach practically all geometry which you can use of binder. Binder after drying and pyrolysis or synthesis, you can receive really your result. It's therefore not immediately print something which are practically a ready product, but it's important to make a mix of these systems. It's some symbol which doesn't work. It's printing, by the way, about printed speed nearly 2 centimeters per hour. You can print layer by layer, layer by layer. It's a setup which you can see in Erlangen if you come to us in the October, November. And pixel size, it can be changed, can be modified. Yes, on the specification we go further, and after that, of course, it was made at our chair. The systems you see, this is nearly 5 centimeters. It's not practical meaning, but it's only example how to work it. Of course, it was made some temperature treatment after printing. There is a selective laser sintering method. This is also important. It was investigated in the University of Texas, and if you see, there are of course several firms and materials which you can print. You can use it with melting and several forms. It's also possible with selective laser sintering to make, but how it's work? It's work. Just a moment. I will show you next slide. But just now, if you think about direct sintering, you need, of course, very high energies of laser until 50 watt, and of course you receive components, several components, and you see density only 70%, the rest of binder, the rest of materials which put it together. And just a moment, it should work. Video doesn't work, sorry. The laser printing in this machine, you make, of course, special forms here. Video doesn't work, but I will explain it. You make sheet of materials which you would like to synthesize. You make sinter with a laser only small sheet, your slice. Yeah. After that, you make this casting again next sheet, net film, and after that you make sintering of the same places. After that, you make again with Dr. Blade again and make again sintering. And in this case, you have with the laser actually grow in 3D direction and product, of course, for medicine, for dental, and so on, also for engine. It's really possible to melt, because with laser you can melt practically all kind of metal, of kind of materials. Also with direct melting, you will ask how it's possible by direct melting. Yeah, it's a press synthesis with direct melting. You start to make a diffusion of some grains all together, and after that you need 1600 centigrade again the heating, the heating. And after that, it's possible to make practically product. As a list of material and which can be used as binder, you can read it later after my talk, or maybe if you have an interest to investigate this system more carefully, or method more carefully, and you see that there are really plenty of products which practically are not possible to melt. It's not possible to melt, but you try to make pre-melting. You try to make pre-melting with heating, pre-melting with laser, and after that you have a system with have enough mechanical properties. Of course, there is the electron beam melting. If you need, for instance, more precision, with electron you can reach more precision as with laser. And of course, for medical implants, people use both technique, additive manufacturing with laser melting or with electron melting. For aerospace, both technique as well. The list of materials you can use, okay, you can go also very hard materials with nickel, wolfram and carbon. And there are, of course, the technology which allow to composite all these techniques, and there are firms who can do it. In this slides, I would like to show you the resolidification. We have actually raw materials in form of filaments, in form of fibers, and if you put it between two mechanical systems and you try to print it, you receive a ready product in this situation, as here. Yeah, you have two kind of fiber, you kind of filaments, and you put it in the nose, and after printed, you can receive, of course, the ready product with extrusion performing. Rubber casting. Also, you can see if you come to Erlangen, actually the system which work with slurry as a paste or gel, because it's some kind of really printing. It's kind of inkjet printing, and there are projects or results or samples which were made with this pasta and gel extrusion. List of products, a list of raw materials with which you can work, of course, and also with polymers. It doesn't matter. You can use practically all components, of course, in form of polycrystals or the sub-microcrystals. And the main problem after which, of course, it's sintering after that. And after that, you can reach density until 95%. Very interesting technique, laminated object manufacturing. Concept, you use pre-sintered glass ceramic tapes, sheets, and you can use it after that with your melting. Look here, for instance, you have an object, you have a sheets, and of course light energy for laser, it's until 340 joule per meter. It's the energy which high enough to make local printing. And if you make printing, you can melting on the separate point of your object. Your computer knows which object should be melted. And people works with velocity, or setup works with velocity of 18 until 120 millimeter per second. It's a really fast process. With this method, you can make, of course, different objects as with simple additive manufacturing. And with materials, you can use, of course, you can use materials from which you have these sheets. And if you have sheets, you can put these materials, of course, layer by layer, melt it, and receive a product as well one. Yeah. Of course, it's possible to use press ceramic papers for the system. It is all published 10 years ago. It's a simple technique, but it's a really interesting thing. And yeah, of course, after that, it's interesting to investigate how much we have of our main component in the system, and exactly the list of materials which you can use for this technique. And at the end, I would like to make some conclusions about importance of additive manufacturing, and exactly the most potential is low cost, rapidity of the process. You can repeat practically one-to-one. Several products is very important for a high quality of a product. And this point is extremely important because you can work from nanoscale until, no nano not, but sub-micro scale until meter scale. You can print buildings. As for instance, in the future, as it was with regard to manufacturing, this is currently dominated substitute machining technology, but it is inevitable that additive process rules or layered fabrication will start to have an impact. And really, it was said 7 years ago, and we need that this importance is higher, and higher. And what is in the future is a vision. Of course, it is possible. It will be possible to make buildings on other planets, as Moon or Mars, for instance, without people which make this processing. You can send a machine there, and after 1 year you can come and go to your house. House is ready, because house is printed really very precisely, very exactly as you have modeled in your computer. That's all from my side. Sorry for not scientific talk, but I would like to say again, after lunch, it's not necessary to mark hard science immediately, but I would like to show you how to make success if you use some ideas from science and physics, laser and ceramic all together, and after that you can produce really very nice products for art, industry, medicine, and so on. Thank you very much.
Questions? Can I ask you something? When we are doing laser sintering, how do you overcome the areas that they are not illuminated by laser? So you have your nanoparticles, let's say metal nanoparticles. How do you secure the efficient sintering across this line of nanoparticles?
It's of course made by interruption of laser beam, or to choose the line which are without interruption. You have saw, maybe you cannot see the video, is for laser melting the crisis. Yeah, it was manufactured, for instance, the cylinder. Yeah, and you should think that you make actually the cylinder. After that you think, okay, I may slice. Yeah, you can go to start the 3D printed of lines which are inside, and so on. Anyway, it's not possible. You are quite right. It's not possible to make completely on an interruption. It's so absolutely necessary.
You have areas that they are not filtered?
Yes, we have areas that are not illuminated. Yeah, with the areas, but with construction of the program, we try to make the areas which are steady state illuminated. Okay. And after that, another areas which also are steady state illuminated. Okay?
Okay. And depending on the deposition layer, you are using, femtosecond if you have a thermal sensitive substrate, or if you don't have a thermal sensitive substrate, you can use even longer pulses, no?
This is a question to Professor Travitsky. I don't know. I think he has no femtosecond laser. His use actually laser continual or nanosecond laser.
So these are not compatible?
No, this is not completely compatible with some double frequency and so on.
So if there are no more questions, let's thanks again.